Let's see if we can find the surface area of a sphere of a given radius, but we're going to use a technique where we think of the sphere as being a parameterized surface. So to begin with, we need to come up with a parameterization of a sphere. We are going to use the well-known spherical coordinates to parameterize. So spherical coordinates where we use a rho, a theta, and a phi to locate points in space. All right. But what we want to do to describe a sphere is we want to pick a very specific radius, a specific rho, like say, let's call it capital R on that. And so if I write these three expressions down, these are the conversion factors to turn rho, phi, and theta into x, y, and z. If I write those down with a specific capital R plugged into the rho, then I have a parameterization. The parameterization would still have a theta and a phi involved in them, but not a rho anymore. The rho will be fixed at R. So if I write R sine theta, cosine, excuse me, that should not be a theta, that should be a phi. Excuse me. So R sine phi, excuse me, cosine theta, comma, R sine phi sine theta. Lastly, R, capital R substituted in there for the rho again, cosine phi. All right, that is our parameterization. The parameterization will be using specific values. Theta, we want to go all the way around. That kind of goes all the way around the xy plane. But for the phi is kind of that tilt angle, and we only want it to tilt from the top to the bottom. So pointing straight up to pointing straight down really only requires phi to go from 0 to pi. That's our parameterization. Let's see if we can use it to find surface area. Surface area for parameterized surface is done using this surface area element, where you compute partials with respect to the individual variables, r theta cross r phi. We often like to use letters like u and v for this, but our letters are theta and phi, so we'll use those. That's fine. So d theta d phi, that's the surface area element we need to integrate. A little bit of algebra to do then. Let's work out these derivatives and some cross products, and let's see what r theta works out to be. So r theta works out to be the following. So we just need to work that out very carefully. When we differentiate this with respect to theta, I get a negative r sine phi sine theta. This derivative with respect to theta is r sine phi cosine theta, and the last bit there has no theta in it, so the derivative of that with respect to theta is 0. Meanwhile, the derivative of r with respect to phi makes the following. Let's see, when I differentiate this, I get negative, no, I don't get negative, excuse me, I get r cosine phi cosine theta. We're differentiating with respect to phi here. R cosine phi again, sine theta. Lastly, r, excuse me, that should be negative, right? So negative r sine phi. Okay. I need to compute the cross product of those two things, but that looks a little bit nasty, doesn't it? So, well, let's do a little trick here. First of all, I notice that things can factor out of this. I can see an r sine phi factors out, leaving with a negative sine theta, cosine theta, and a 0 on that. And I'd like to factor something out of this, but I only see an r that factors out. I do see a cosine phi and a cosine phi, but no cosine phi on that last bit. But you know what? Let's factor out a cosine phi. We can use this trick. It's going to work. Cosine theta on that, sine theta on that, negative, well, okay, if I factor out a cosine phi, then I really should write sine phi over cosine phi here, but that makes tangent phi, and that's actually going to be easier to work with. So the cross product looked a little daunting at first, but I think it's going to be not so bad. Let's work it out. R theta crossed with r phi makes the following. Now when I do the cross product, I will factor those expressions out. I have two r's, so r squared sine phi cosine phi. Let's set up the cross product as a determinant. Okay, so that's going to be a negative sine theta, a cosine theta, and a 0. And for the next bit, I'm going to have a cosine theta, a sine theta, and a negative tangent phi. All right, let's see if I can work that out. So let me put a little line here to separate out my writing, shall I? So that makes r squared sine phi cosine phi, excuse me, times, let's see, when you do this cross product, what do we get? For the I component, I'm going to get negative cosine theta tangent phi minus 0. For the j component, I'm going to get, let's see, sine theta times this minus that. But remember, when we're doing the j component, we have to negate, so that's actually going to be negative. What's that make? Negative sine theta tangent phi. All right, running out of room there, so let me write it down here. For the k component, negative sine squared minus cosine squared. Well, by a trig identity, that just makes the number negative 1, right? So I'll just squeeze that in here. All right, so that is this r theta crossed with r phi. Let's find the magnitude of that vector. All right, r theta cross r phi magnitude makes the following. Let's see, this bit's still there. R squared sine phi cosine phi. Okay, now of course, because I'm taking a magnitude here, I really should be taking absolute value of all that, right? Okay, I know some of that might be positive, but let's be careful. So when I take the magnitude of this, let's think carefully about how that's going to work out. When I do this thing squared plus this thing squared, that turns into something nice. There will be a cosine squared plus sine squared of theta in there that can be factored out, and that just makes the number 1. So all that makes together is, of course, there's a square root here because of the magnitude. I'm going to have a tangent squared phi on that, okay? But there's still this z component there, and that's going to be plus 1. But that expression might look familiar to you. That's actually the secant square root of phi, isn't it? Okay, all right, that's fun. So secant square root of phi, all on the side of a radical, of course. And so what that makes is, altogether, that makes r squared. Okay, now that doesn't need to be inside of the radical, does it? Absolute value of sine phi. All right. Absolute value of cosine phi, but then times the square root of the secant square root of phi, which is the absolute value of 1 over the absolute value of cosine phi. These things, actually, let's use a different color here. This thing here cancels with this thing here. And that's it. That's the whole thing. That's all we're left with. And so that is the only thing that we need to integrate now. Okay, I think I might have just enough room to squeeze in the final calculation here. So the surface area that we want is the following. The surface area is equal to this expression integrated r squared magnitude of sine phi. You know what? Come to think of it, I don't think we need a magnitude on that, do we? Because phi is ranging from 0 to pi, and we do know that sine phi is positive in that range. So let's just write down the appropriate thing here, sine phi. All right. Now don't forget the r theta crossed r phi has to have a d theta d phi at the end of that. All right. Theta is going to range from 0 to 2 pi, whereas phi is going to range from 0 to pi. All right. Now, notice something here. There is no theta in this whatsoever. All right, so that is a constant with respect to theta. So the only effect of the theta on this is to just multiply the whole thing by 2 pi. All right, because we're integrating a constant. And then we're going to be integrating sine phi. All right. Now, I'll let you work out the rest of the details on this, but when you integrate sine phi from 0 to pi with respect to phi, what you're going to get is the number 2. You can work out the details on that. And so that makes 4 pi r squared, an expression you may have seen before. I think we have a nice little derivation of it now.